Hi, I'm Ben Canning. This micro lecture is on temperature. As always, you need 3 or more bullet points worth of notes, a 1 to 2 sentence summary, and to do your follow-up questions on Google Forms. All right, so we've talked about the idea that thermal energy is the energy of warmth, and when that warmth is moving from one object to another, we call that heat. But then what is temperature? Well, that's what we're going to focus on in this video, as well as 3 common temperature scales. So to talk about temperature, let's imagine some air. We imagine that we zoom in on this air so we can see the actual like air molecules moving around, so the oxygen and nitrogen and carbon dioxide, etc. And they're moving around. And if that air is cold, then they'll be moving around because it's still gas, but they're not going to be moving as fast, meaning they'll be either physically like traveling in translational motion, meaning like side to side movement or up and down or in a round kind of thing. Or they'll be vibrating or they'll be rotating at a slow or moderate speed. Now, as we heat that air up, what we'll notice is that those particles move around a lot more, either again physically by traveling one place or another, or vibrating or rotating a lot more. Now notice that they're all moving in random directions, so even if this one is traveling this way, we've got that balanced out by others traveling the opposite direction. This air isn't going anywhere. It's not like wind where it goes from one side of the room to the other. These molecules are really just staying in pretty much one place, or one general area, but they're moving around within that area. So here we've got this idea that temperature is really a measure of how fast molecules in something are moving or vibrating or rotating. If it's a gas or a liquid, they might be actually physically moving around, like in this image. But if it's something more like a solid or even some liquids, you're going to see a lot more vibration and rotation instead, because molecules can't just move around in a solid. So officially, what that means is temperature is the measure of the average kinetic energy of the molecules in something. So if we look at how much kinetic energy this guy has, and this guy, and this guy, and this guy, and really all of them, and we average them all out, that would be essentially the temperature. Not exactly, but it's proportional to it. So we scale it up or down to make it a nice number. And so that's what temperature is. Now, this image is a little bit inaccurate in that each molecule won't actually be moving at the same speed. So we say average because this one might be moving a little slower than this one and might be moving a little bit slower than this one. So what we would see is that some are moving very fast and some are moving very slow, but the bulk of them are kind of near that average temperature or average measurement. So we measure temperature in 3 common scales nowadays, but lots more were created historically. Fahrenheit scale is one we're most familiar with in the US, measured in degrees Fahrenheit. It's rumored that to make any scale, first of all, what they often do is they pick 2 benchmark temperatures that can be reliably determined, or recreated, and then they set one of them at, let's say, a 0 mark and the other at 100 or maybe at 200 mark, and they decide how many like divisions they want in between. So you can make your own temperature scale, having the temperature of, let's say, your favorite cup of coffee be the hot end and your favorite ice cream at the low end, and say you want 10 degrees in between, and so you'd have 10 different marks in between. That's all a temperature scale is. It's a little arbitrary of sorts, but our goal is to make it reliable. So even though if it is a little bit random in how it's determined, we can recreate it anywhere in the world very easily. So Fahrenheit, rumored to be based on an icy saltwater mixture, and body temperature, but there's a video that explores the myth around that a little bit more. Regardless, in Fahrenheit scale, we know that, or hopefully remember that, water boils at 212 degrees, it freezes at 32 degrees. That makes a very nice 180-degree difference between those two. And then the coldest temperature that is possible, called absolute zero, and we'll get into why it's called that in a little bit, would be at negative 459 degrees Fahrenheit. Now, Celsius, realizing that so much water is present here on Earth, and that's very easy to kind of use as a benchmark, decided to use water boiling as one of his major points and water freezing as one of his major points for determining the scale. So he set one of them at 100 and one of them at 0, or at least that's how it came to be eventually. And so then set that there would be 100 marks in between them. So that's what the Celsius scale is based on, namely water boiling and freezing, which is why those come out to very clean numbers. In Celsius, we say degrees Celsius. And one thing to note is that these numbers will end up being a little bit smaller in number, but larger in size than in Fahrenheit. So Fahrenheit has a lot more kind of individual marks versus Celsius. Each degree is significantly more in terms of temperature change. Last but not least, we have Kelvin. So you'll notice here that we have this idea of absolute zero. There's a video on it more later, but basically this is the least amount of kinetic energy molecules can have. It's been determined that there's kind of a minimum temperature things can get to. And they figured out that that would be around 273 negative Celsius. They did the conversion to figure out what that was in Fahrenheit. Well, a guy named Kelvin came along and he said that's kind of silly to, and he was the one who actually figured this out. He said it's kind of silly to have negative temperatures. That doesn't really make sense. So he created a scale that would get rid of negative temperatures. Namely, he took the Celsius scale and said, well, instead of starting it at zero at the water freezing point, we're just going to put zero at absolute zero, but use the same size degree marks. Now in Kelvin, we don't call it degrees, we just say Kelvin. So it'd be 373 Kelvin instead of like 100 degrees Celsius. So absolute zero is set at the zero mark, and then everything else is just scaled up from there. So 1 degree Celsius change is the same as 1 degree Kelvin change, but the numbers levels will be a little bit different. Now, in science, we only use Celsius and Kelvin. We don't use Fahrenheit. And to kind of recap all of these, we've got this nice kind of temperature image here or thermometer image here to help you imagine it a little bit better if the grid method wasn't as good. So Fahrenheit, smaller degrees, 180-degree difference between water boiling and freezing. Celsius and Kelvin, we've got 100 number change or magnitude change between the two. But with Kelvin being set at 0 being absolute zero instead of 0 being the temperature at which water freezes. That's it for this one. 3 more bullet points worth of notes, a 1 to 2 sentence summary, and please do your follow-up questions on Google Forms.